So, today we want to go over from theory of free convolution for compactly supported probability measures to any probability measure. Okay, so in the last chapter we developed a theory, mainly analytic theory, by using the R transform to describe the free convolution of compactly supported probability measures. And for compactly supported probability measures, the probability measure can be described by its moments. So this fits very well in our frame. If we have arbitrary probability measures, of course we have a problem, because such a measure might not be determined by its moments, or it might not have all moments, and then of course we are falling out somehow out of our usual analytic frame. And the only thing we are left with is more or less analytic machine. Okay, but still this can be done, so we want to talk about the free convolution of arbitrary probability measures, of course on R. And actually, we will also make a shift in our analytic tool. We will still talk about the R transform, but we will go over to another object, which is called the subordination function, which is really much better in this context. Subordination function. Okay, and quite a bit of today will be to convince you, to give you an idea what the subordination function is, but also to convince you that this is a better analytic object than the R transform. Good, but let us first start with some remarks. So what we want to do. So we want to extend our theory from last chapter to arbitrary probability measures. So we want to extend the theory of free convolution to arbitrary probability measures. Okay, and then, as I said, there are problems. We cannot just talk about moments and cumulants and just translate this. And so it's not even clear how directly to define this object. And there are essentially two possibilities, two approaches for doing this. So in order to define the free convolution of arbitrary probability measures, such a case, there are mainly two possibilities. The first one is trying to extend what we did up to now. The definition of the free convolution was that we realize our probability measures by operators which have the given distributions, and then if the operators are free, we take the sum. Okay, we could now do the same, but of course now we have to realize a probability measure which might not have moments by an operator, and this means we really have to go over to a frame where we have unbounded operators. So we could do this with unbounded operators, but then there are a lot of technical issues. Okay. So that's an approach which was followed in the beginning, but we are not doing this, but I want to mention it because it's a possibility. So we can realize we have nu as distributions still of some operators, but then they are not living in a star probability space. Yeah? So, but you have to choose the frame more carefully. So in particular, it will be unbounded operators, let's say x and y, on Hilbert spaces. Okay, I wanted up to now to realize our operators on Hilbert spaces, but essentially if I have a star probability space, then with DNS construction, I can realize this as bounded operators in the Hilbert space. So bounded operators are nice. So up to now we essentially dealt with bounded operators, but now in the general case one needs unbounded operators, and this realization must in a sense be a nice one. So the technical term is that
operators are affiliated in finite Neumann algebras. Okay, you don't know it means, at least not now. We will talk about Neumann algebras later, but we are not going to use unbounded operators. Okay, but so this can be done, so we can realize the given distributions as unbounded operators, and we can also choose them to be free. Of course, then we also have to define what do we mean with freeness for unbounded operators. So all this can be done. Such that x, y are free. And then, of course, we define the free convolution of our two measures as the distribution of the sum of our operators, which of course is then also an unbounded operator, x plus y. Good. Okay, and actually this was the first approach to defining the free convolution in such a setting. This was done by Berkovich and Voiculescu in 1903. So this really was the way which was followed by Harry Berkovich and Voiculescu in 1993. Good. Okay, but what we want to do is we want to try to extend the analytic description, which we had in the case of compact supported measures, to this case. And then the idea is, of course, I mean, what we always have is the Cauchy transform, also for unbounded operators, and then we could try to define the R transform as an analytic object by the relation between Cauchy and R transform, and then convolution is given by additivity of the R transform. Good, so this means we should try, that's what we want to do, try to extend the approach from the last chapter. This was the approach that we defined the R transform. So, I mean, we can describe and we can define the free convolution by the linearity of the R transform. So if you have an R transform, then we are in a good situation. So while I define the R transform by this equation, which says that the Cauchy transform and R of z plus 1 over z are inverses of each other with respect to composition. Okay, so we can hope, I mean, the Cauchy transform, that's a crucial point. This is defined for any probability measure, and it's a nice analytic object. So we can use, or we hope to use this equation for defining the R transform, and then we define the free convolution by saying that the R transform is negative. And defining free convolution of two measures requiring that the R transform of the free convolution is given by the R transform of the first measure plus the R transform of the second measure. Okay, and of course, I mean, one has to think about the domain of definition, because already last time I said the R transform cannot be defined everywhere, and that will be one of the main problems, which is not so good, but it will be become better if you use the subordination. Good, okay, so this was an approach which was followed later in the first approach, and so this was done around maybe 2005 and later by two groups. One is Chistyakov and Götze, and the other was Levinsky, and Berkovich. Okay, but in these approaches already there was this change of perspective that the R transform, maybe one needs it as an intermediate object, but for the final description we go over to the subordination function. So,
That's maybe the crucial point of this approach here. So, however, instead of the R transform, one describes theory in terms of a so-called subordination function, which is called omega, and which has much better analytic properties than the R transform. Maybe I should give you now tell you what is the subordination function, or how do we make this transition from the R transform from the subordination function. And on a formal level, it's the same description. Right? It's just introducing a new object which formally describes the same information, but later it will turn out to have better analytic properties. Okay, so let me do on a formal level first. We write our description in terms of the R transform in this subordination function. Okay, so let us write the R transform description into a subordinated form. Now at the moment just on the formal level. No? So I mean this can be done also in the case of compactly supported measures, where I mean these formal manipulations make sense as formal power series, or at least power series converging in some domain. No? But I mean at the moment we are not caring about convergence issues. So just on the formal level. Good. And so the point is that we have subordination functions, and actually we have two of them, and I just give them to you right away, and then we check what property they have. So now we have subordination functions. I have two of them, so I call them omega 1 of z. So what is this? This is something which involves the R transform and the Cauchy transform, so it's z minus. Okay, and it's a 1, so this means it's the formulas are not symmetric in the two measures, but I mean one involves here the second measure, 1 mu, and then I have here the Cauchy transform mu plus mu of z. Okay, and the second one is the same. I just exchange the two measures, and here I have mu, and of course here this is of course symmetric. I have again convolution. Okay. So you see this is a function which involves also the object which we want to define. Okay, so I mean, writing it like this I can only do after I have defined those objects. But on form, for compactly supported things we have this. And you see, this subordination function is not an object which only depends on one of the measures. It's really an object for a pair of measures. The R transform you can define for a measure, and then it is additive if you want to take the free convolution. The subordination function is only defined. You want to do the free convolution of two measures, and then for this problem, you have two subordination functions. Good. Okay, but what are they good for? And for this, let us check the property for the Cauchy transforms. Namely, it says that the Cauchy transform of this is subordinated to the Cauchy transform of mu with the help of this function. Okay, so let us calculate this. So let's say G, I know this by G. No? G is the Cauchy transform of mu plus mu. And then let us calculate what is G mu of omega 1 of z. No? I'm claiming that this will be G of z. No? Okay, but let us check whether we get this. Okay, so what is so
G mu, what is this? Omega 1 of z, we just have used definition, this is z minus mu of G of z. Okay, and now, of course I have to do some reformulations. You see I have here the Cauchy transform of mu plus nu, and I have here the R transform. And of course Cauchy transforms and R transform are more or less inverses of each other, but of course I should use the same measure. So this corresponds to this, so I would need the R transform which also corresponds to this. But on the R transform, I have this additivity, so I can rewrite this here. I have here, I can rewrite it as R mu plus nu of this argument. Okay, but this is the sum of this and this, so I should subtract the R mu of G of z. Okay, this is just the additivity. Okay, now this term is a nice term, because this corresponds to the measure mu plus nu on the R transform and for the G transform, and I mean R plus 1 over z are inverses of each other. So if I plug this, if I take this, then this is z plus 1 over G over z. Because R of the Cauchy transform minus 1 over the Cauchy transform is equal to z. That's just the equation that the R transform plus 1 over z and Cauchy transform are inverses of each other. Good. Okay, so we have this. So now let's see where we are. So all this is the argument of G mu. And what do I have here now? For G mu, you see I have here z, and then minus all this. So this cancels this set here, and here I have a minus, and minus, this gives a plus, so I have here a mu of G of z, and then I still have this term with the minus sign, minus 1 over G of z. Yeah, but now again I have here a situation, G of z is here just an argument, and I have here G mu, and here I have R mu of the argument, minus 1 over the argument, but those guys are again inverses of each other, so this means what I get here is just G mu, just the argument. The argument is G of z. Okay, so you see I get something very simple here. So namely I have now all this here is just G of z, and finally I have the G of z is G mu of this function omega. And this is the subordination. The function G is subordinated to the function G mu by this function omega 1. Okay, so what we see from this calculation is that we can express the Cauchy transform of the free convolution as the Cauchy transform of one of the measures, but we have to shift the argument by this function omega. And this is called subordination. This is called that G is subordinated to G mu. And the omega is the subordination function. So hence G subordinated G mu via subordination function omega 1. And this just means what we have exactly observed, namely that G of the free convolution mu plus nu and the argument z is the Cauchy transform of mu, but we have to change the argument to omega 1 of z. Okay, and of course there's asymmetry here. I have here used mu, I could also use nu, and of course omega 2 is the subordination function for this. Same argument, just it's changing mu and mu. We also get the G mu plus mu of z is equal to G mu of omega 2 of z. Good. Okay, so you see, we can rewrite essentially our description of the free convolution by saying that the R transform is additive. Also by saying that there are functions omega 1 and omega 2 such that the Cauchy transform of the free convolution is subordinated to one of the starting equations. Good, but of course, I mean, at the moment, the definition of our subordination functions is in terms of the R transform, and this is very complicated. Actually, this is something, I mean, which we essentially want to define, so this doesn't look so useful. Maybe we cannot really calculate it, at least it's not clear how to use this as a definition of the free convolution in particular, because it still involves the R transform. No? Okay, but now we want to rewrite this definition in the form that the R transform disappears. No? So at the moment, this is a nice formula, but the omegas are described in a very ugly way. Looks even more complicated than the R transform. The R transform is a complicated thing. Of course, that's not. If this would be everything you could say, then it would not be very useful. But one can do better. So omega 1, 2 are defined in terms of the R transform, R mu or R nu. So this does not really give anything new, but we can reformulate this. Reformulate the defining equations in a form not involving the R transform, not involving the R transform. Okay, so namely, we have. And again, I'm playing around. I mean, I'm just playing around at the moment on a formal level with all those formulas. Oh, so here. Write down some equations for omega 1, omega 2, which do not involve the R transform. I mean, the Cauchy transform is okay. I mean, the Cauchy transform is a nice object. The R transform is analytically not so clear, so we would like to have a formulation which does not use the R transform, or taking the inverse of with respect to composition of the Cauchy transform. That's the point. I mean, for the R transform, we have to take the inverse under composition of the Cauchy transform. Taking the inverse is something which is not so good to control. Good, so let us see what can we do with those equations. So let us look on taking the sum of the two subordination functions and just using those equations there. So omega 1 of z, so this is z minus R mu of g of z plus, and omega 2 of z is the same with z minus R mu of g of z. Okay, now if you take the sum, of course I have here R mu plus R mu, and this gives me R mu plus mu. So what I have is z plus z minus, free convolution is additive, so this here is R mu, free convolution mu, and the argument g of z, and again this here, I mean, the R transform plus 1 over z is the inverse of the Cauchy transform, so this here is just 1 over g of z. So this minus this is equal to z. That's again the relation between R and G. Good, so you see I have this, and now I have got rid of the R transform. I still have here the Cauchy transform of the free convolution, and if I want to use such equations for defining the omegas, of course I should not involve the free convolution, no? Because I want to define it. Okay, but here I have the Cauchy transform of the free convolution, but we know that I can write this also as the Cauchy transform of one of them and the origin and one of those subordinating functions. So I can also write this here as 1 over g mu of omega 1 of z. And so what we get from this is now actually an equation which involves omega 1 and omega 2 and only known quantities. Quantities and nice quantities of mu or of nu. So here I have one equation, and of course by symmetry I have another one. So at the moment I have two subordination functions, so I would need two equations for defining them. So what I have seen here is omega 1 of z plus omega 2 of z. Let me bring it on the other side, minus 1 over g mu of omega 1 of z. This is equal to z, or equal to this z. Okay, in the same way, if I just, instead of using here g mu of omega 1, I can also use g mu of omega 2. So I also have omega 1 of z plus omega 2 of z minus 1 over g mu of omega 2 of z. This is equal to z. So you see we have two equations for our two unknown functions, and they involve essentially g mu and g nu. That's the information about our measures of mu and nu. And we can also maybe even eliminate one of the omegas and just get one equation for, let's say, omega 1. Okay, so let's do this. And you see the Cauchy quantity which we have here, g mu, Cauchy transform. What we have here is 1 over the Cauchy transform, and then maybe here we also subtract the set. So, yeah. So maybe instead of g, I use another quantity which I call h, which is just a variant of g, but the one which makes the equations nice. So I define h mu of z as 1 over the Cauchy transform minus z. Okay, now let us see what we get from this. So let me take first equation. So then we have, let me write omega 2 of z. So I take this equation, I bring the omega 1 on the other side, and this also on the other side. So omega 2 of z is z plus this guy plus 1 over g mu omega 1 of z minus this here. Minus omega 1. Minus omega 1 of z. And so you see what I have here exactly is this function h at the argument omega 1 of z. H is 1 over the Cauchy transform minus the argument. So what I have here is actually z plus h mu of omega 1 of z. And so what I get here is this equation, omega 2 of z, is this. And now you see I can now eliminate omega 2 in terms of omega 1. Here I have written omega 2 in terms of omega 1, which means I can eliminate out of this equation, let's say, the omega 2. And then I get an equation which only involves omega 1. So, of course, I get the same. I can do the same. Here I have written omega 2 in terms of omega 1. The other way around, I can also write omega 1 in terms of z, in terms of omega 2 as h mu omega 2 of z. And then I can use this equation to eliminate this omega 2. So what I then get is omega 1 of z This is Z plus H nu. The argument omega 2 of Z I replace by this. So I get here Z plus H mu of omega 1 of Z. And this is now here crucial equation. So this is now, you see, this is now a fixed point equation for omega 1. Omega 1 is some maybe complicated function applied to omega 1. This is a fixed point equation, but what I use here is just this function h for nu and for mu. And h are just some easy variant of the Cauchy transform. Okay, so this fixed point equation now just involves the Cauchy transform, maybe some easy versions of it, but it does not involve taking the inverse under composition of the Cauchy transform. So it does not involve the R transform. Yeah, okay, and I mean, so it turns out that this equation here is much better to deal with than with the defining equation for the R transform. Okay, so maybe, I mean, maybe this is not so clear, but you should believe me, and I hope to show you an example that at least the omega 1 which we get out of such equations really is a much nicer analytic object. So that's the point. I mean, this here is a fixed point equation. The fixed point equations are usually nice if we have some control over this side, and that's what we can do. So this is really a fixed point equation which one can nicely control, and it will turn out that the solution of this equation is really an analytic function everywhere, not just in some small domain. Okay, and in order to see, I mean, what is the difference between this and the R transform formulation, let us look again at the example from last time, the convolution of the Bernoulli with itself, which we calculated by the R transform machinery, and let us see how this here tells us what we should do in this case. Of course, we should get in the end the same solution, but just the way of getting it and formulating it are really different. So let us do this. So this here is really, I mean, this is the crucial equation, omega 1. And if I have omega 1, then of course I have the Cauchy transform of the free convolution, because then it is given in terms of G mu and this omega 1. Good, so we look again at this example from last time, where we had the free convolution of P Bernoulli, and in this case we really could calculate explicitly the result. The result was the arc-sine distribution. And mainly, I mean, what we want is the Cauchy transform of the free convolution. If we have this, then we also have more or less the next. Consider this example. So let us do this example again. So we consider the example. So this was for 14. And we do it now from this subordination perspective. So mu and mu are the same. Measure now. So mu and mu are the same, and both were this Bernoulli, which means a discrete measure. Okay, and of course we calculate the Cauchy transform. The Cauchy transform of this is very simple. So this G mu of Z. This was just Z divided by Z squared minus 1. Oh, okay, this is very simple. Good, and now we need this H transform. Maybe I write it down again. So H, I measure mu of Z. This was 1 over G mu of Z minus Z. Yeah, okay, so this, I mean, before we said, okay, we should calculate the inverse of this guy to calculate the R transform. Now we say we're not calculating the R transform. We want to look on this equation, which involves this function H. So we should now calculate H in this context. Okay, so this means this H function, which mu of Z. So what is this? This is 1 over G. Yeah, 1 over G mu of Z minus Z. G mu is this, so 1 over this is Z squared minus 1 divided by Z, and then we are subtracting the Z. So you see, it's getting very simple. Z squared divided by Z is just Z, which cancels this, and we just remain with 1 over Z. This is just 1 over Z. So the Cauchy transform is this, and now what we should do is, what we have seen before, we can now write the Cauchy transform according to what we did above, here above. Yes. That we can write the Cauchy transform, and that's the Cauchy transform of mu plus mu. Oh, that's what we want. That we can write this in subordinated form to G mu, so it's G mu of omega 1 of Z, and actually I mean, of course omega 1 and omega 2 are now the same, so because mu and mu are the same, so things are further symmetric, so that we just call it omega, omega of Z, where this subordination function has to be determined as a solution of this equation. So we know we can write the result, the G of Z, in which we are interested, we can write it as G mu of omega, where is omega, so where the subordination function omega, which actually in this case is the same as omega 1 or omega 2, they are the same by symmetry. So just call it omega. So this is determined by this equation star as follows. So let us write down this equation now in our case. So what does it say? It says omega of Z. This is equal to Z. And I should take the H transform. But H is just actually, I have forgotten here minus sign, Z minus 1 over Z. So this is minus 1 over Z. So I have here minus 1 over, and what is the argument? The argument is now Z plus, and then I take again the H transform of the other measure, but it's the same. So I take again the minus 1 over Z. So I have here minus 1 over the argument, and now the argument is the subordination function. So it's omega of Z. So you see I have here an equation for omega of Z. And of course, again I get a quadratic equation. I mean, for this Bernoulli thing, I mean everything are quadratic equations. So from this point of view, it might not be clear. This is just another quadratic equation. So why is this better as the one for the R transform? But let us first look on this equation and solve it and see that we really get what we have to get. So this is now a quadratic equation, which maybe let me write it. Okay, so what is a good way? So maybe bring this on the other side, and here I have Z minus omega of Z. This is 1 over Z minus 1 Z. So if I multiply this tells me here, so this tells me that Z minus omega of Z multiplied with Z minus 1 over omega of Z, this is equal to 1. And if I multiply this out, I get Z squared minus Z omega of Z plus 1 over omega of Z. So this is this times this, and this times this, and then I will remain this plus omega of Z times 1 over omega of Z, which is 1 plus 1. And this is equal to 1. So you see the ones go away. And then actually I can also divide by Z. We have here now 0. I can divide by Z. Because we are not at the 0. We are looking for Z, let's say, somewhere in the upper half plane or so. So Z is not equal to 0, so no problem with this. And then, yeah, we remain with the equation. So, yeah, this here is equal to Z. So omega of Z plus 1 over omega of Z is equal to Z. Okay, so that's the same equation as this one. And so now we see this is a quadratic equation, which of course we can solve. Which has the solution. Yeah, omega of Z is equal to Z plus Z squared minus 4 divided by 2. And again, of course, there are two solutions. I have to choose the right one. And I mean, if you look on my definition of omega, you see that at infinity it should behave like Z. Infinity, I mean, Cauchy transform maps infinity to 0. The R transform maps 0 to 0. So close to 0, we are close to 0, so that's the leading order term. Close to infinity. Okay, and for this we need the plus and the minus. Yeah. Plus, because omega of Z must behave like Z for large Z. Okay, so we have a solution. And now, of course, we can plug this in this formula, and this gives us then the final solution for G. Good, so let us plug in the omega in this equation and then see what we get. Of course, we know what we have to get, but let us check to see if it's the same. Then we have, so what does the subordination formulation tells us? That we get G of Z as G mu of omega of Z. And G mu, this was our starting G, this was the Z divided by Z squared minus 1. So this means we have here is of course then the argument divided by the argument squared minus 1. Good. And of course I can divide by omega of Z. So this is 1 divided by omega of Z minus 1 over omega of Z. And you see our quadratic equation for the omega of z was more or less this combination, but not with the minus sign, but with the plus. But at least I can replace this here by z minus this. So plug this in. So I have the 1 divided. So this here is omega of z plus z. Or minus. Yeah, I bring this on the other side, I bring this on the other side. So this means minus 1 over omega of z is omega of z minus z. So I get another omega of z. I have here 2 times omega of z minus z. Okay, now you see this goes nicely with our solution, because the solution is this here divided by 2. So 2 times the solution. This 2 goes away, and then I have here the z, which is cancelled by this z, and I just remain with the square root. So what I have here is just 1 over the square root of z squared minus 4. And of course this is the result which you also calculated before. This is the Quotient transform of the arcsine distribution. So you see, I mean, the omega 1. And some more other terms, but this goes nicely together. So, which increase with our side from 414, which gives, of course, now the arcsine distribution. Mu as the arcsine distribution. Which you get if you apply the Stieltjes inversion formula to this Quotient transform. Good, okay, so I mean, this tells us, shows us that we could, instead going to the R transform, we can also do the calculation like this and just taking this equation. But of course, this equation, I mean, solving this equation is solving the quadratic equation, which is the same as solving the equation for the R transform, which is also a quadratic equation. But still, I insist on saying that the solution of this is better than the solution of the other quadratic equation. So maybe now I should somehow convince you that there is really an advantage over, let's say, this solution than the solution which we get via the R transforms. So, the question is, but what is the advantage of this solution, let's say omega of z, so this is z plus z squared minus 4 square root divided by 2. So what is the advantage of this solution over the R transforms, which we calculated in 414 over the R transforms? Let's say the R transform of the free convolution, also of the final result. So the R transform of the arcsine distribution. So this is 1 plus 4z squared minus 1 divided by z. So this was the solution. I mean, looks very similar, square root here, square root here. So what is really the difference? And the difference is that actually this can be extended to all of the upper half plane, but this cannot be extended to the upper or the lower half plane. So these solutions, I mean, if you do it for the compactly supported case, then essentially the calculations which we did here can be justified. I mean, we know the R transform is the solution in a ball, small ball about 0, and the omega is also an analytic function there. Okay. But the point is that this can be extended analytically to all of the upper half plane, and this cannot. So this. all the calculations which we did are rigorous, even rigorous for analytic functions. So I mean, they show that omega and r are analytic functions on some small domains. I mean, in the compactly supported case for bubbles. So note that these formula calculations which I did can be made rigorous on the domains in C plus C, but omega and r are different in respect of extensions to all of C plus or maybe C minus. Oh, okay. Yeah. So let us first look at omega of z. So this is z plus the square root of z squared minus 4 divided by 2. Yeah. Okay. So where is this defined a priori? I mean, what we wrote down. It's not there anymore, but when we defined at the beginning, it was omega of z was z minus the Cauchy transform, and the Cauchy transform maps 0 to neighborhood of infinity. So this means this is a priori defined in neighborhood of infinity. So this which is a priori defined only for large set, but that is defined as an analytic function. So it's an analytic function for large set, but this analytic function is given by this formula, and actually this formula can be used to extending it to all of C plus, because this formula makes sense as an analytic function all of C plus. So this can be extended by this formula. Formula to C plus. And of course one has to choose the right branches of this. So this is the square root in a complex plane. I mean, of course you cannot define the square root everywhere in a complex plane. You must have a cut somewhere. Okay, but we can choose a cut so that, I mean, there is no problem with this formula in the upper half plane. So by choosing branches for, I mean, actually z squared minus 4, of course, is z minus 2 times z plus 2. So the square root of z squared minus 4, we write z minus 2 and z plus 2. And of course, I mean, the square roots, they have problems around 2 and minus 2. Okay, but if we want to stay in the upper half plane, we have no problem. This can be defined in one of the upper half plane as an analytic function, and this can also be defined there. And then this can also be defined. So only around 2 and minus 2 there are problems. So this means we cannot really have it in the upper and the lower half plane, because around these points there are problems. But otherwise it's okay. So we can choose branches without cuts in C plus. And so this means what we get here is really an analytic function defined everywhere on C plus, and you can also check that this is also mapping to C plus. It means omega is actually a mapping from C plus to C plus is a nice analytic object. sense, it behaves like a Cauchy transform. The Cauchy transform is also an analytic function from the upper to the lower half plane. And that's what we want of our objects. Not just functions defined in some domain which might be hard to control and might depend on the probability measure which we consider, but a function which is always analytic on, let's say, the upper half plane. So you really can control it. Okay, so omega is very nice, but R, on the other hand, this has problems. There, of course, we also have a formula in some domain, but this formula cannot be extended. So we have this formula here. We could define in the neighborhood of 0. Okay, there we know it's an analytic object, analytic function, and it is given by this analytic formula in the neighborhood of 0. So this is arbitrary, undefined, for small set. This formula actually not be extended, not to the upper half plane and also not to the lower half plane. Can by this formula not be extended to C plus or to C minus. Okay, maybe I should think, the R transform is actually something which I would like to define on C minus. Up to now we define it on a ball about 0, so it doesn't matter C plus or C minus. But if I want to go further, like for the Cauchy transform, the Cauchy transform was also defined outside a ball of a radius, but if I go more general, I can define it on the upper half plane. And because the Cauchy transform and the R transform are inverses of each other, and the Cauchy transform goes from the upper to the lower half plane, the R transform should really be defined on the lower half plane. Okay, so this means really I would like to have an extension to C minus, but this cannot be done because, this square root here, 1 plus 4 set squared, this really has problems, not on the real line, but it's exactly the point I over 2 or minus I over 2 where I have problems. And in the neighborhood of this, I have no possibility of giving sense to this as an analytic function. Also, since we do not have much as 1 plus 4 set squared, square root of this, the problem is where this is 0. The square root of set about 0, that's a problem. So I have to have a cut somewhere. Okay, of course this is equal to 0 if set is plus or minus I over 2. So in the neighborhood of set is I over 2 or set is equal to minus I over 2. Okay, and this means this here prevents it from being extended to something in the upper half plane, and this prevents it from being extended to something in the lower half plane. So I can extend it in some ball, but if this ball hits those points, then I'm getting problems. There's no extension. Good. Okay, so this hopefully makes clear that even though on the surface it looks very similar, having the omega is this, and the R is this. It's not clear what should be the difference, but there's really a very crucial difference. Right? It's the analytic behavior of those solutions. And so what we have seen here in this very specific example now actually is true in general. And of course that's something which we would like to understand a little bit better. So let me first make this remark. What we observe in this example is true in general. And now with general, I mean really any probability measure, not just for compactly supported. Of course, if my measure is not compactly supported, I might not be able to define my R transform anymore in balls, which are small, because this goes with the power series expansion where I have two cumulants. If I have cumulants, I have moments. Okay, so if I don't have moments, then there cannot be such power series expansions in balls about zero. So this means, in general, I will not be able to define the R transform really in balls about zero, but there are other domains in the lower half plane where it still can be defined. Okay, so what we have in general still can define the R transform, not necessarily in balls, anymore, but in some wedge-like regions. And I will be more precise about this soon. Wedge-like regions. And as I said, in principle, we wouldn't like to have it in C minus. So there are some regions in C minus where we can define it, but from there it cannot be extended analytically to all of C minus. At least not in general. This cannot be extended of C minus. Okay, but the subordination functions on the other hand, which we essentially define by this fixed point equation, can really be defined everywhere on C+. They are analytic function everywhere on C+. So this means what one has to show is that this here has a solution in everywhere in C+. So it's really understanding this fixed point equation. This is a nice fixed point equation which really has solutions not only in some strange domains, but really everywhere on C+. So, part 2, subordination function, this is nicer, much nicer. So, subordination function, subordination functions, which are defined by fixed point equations. Can always be extended to all of C+. Another way of saying this is that this fixed point equation really has a solution, unique solution for all of, for set in Z+. Okay. Good. And so that's something which we have to understand. Okay. I mean, I want to give you some ideas of proving those things, but of course, I mean, probably it's clear that the technical details will be more involved than in the case of compactly supported. But the main ideas, I mean, the ideas are somehow similar to what we had before, And then of course this extension. This is the crucial thing. So I mean, I want to give you the main idea what kind you use. And of course, again, you use important theorems from complex analysis. No? So, good. But maybe first, let me start. He's talking about the R transform. No? So again, I mean, we start with the R transform, which can be defined somewhere. No? Okay, and we should now find out where can they be defined. And it's not balls anymore, but it wedge-like regions. So let me first define the regions where we can define the R transform. Definition. So for alpha, beta, greater than 0, we define some region. And we call this a truncated Stolz-Angel. By this is the set. So that's a set in a complex plane. Depends on alpha and beta. Alpha and beta are positive numbers, and then we take complex numbers to form x plus iy. X and y are real and imaginary part. Those guys should be in C plus. And they are defined by conditions that alpha times y is greater than the absolute value of x, and y is also greater than beta. Okay, maybe picture says more than definition. So here's a complex plane. And this guys, so I mean y is greater than beta, so that's truncation. So in principle, I mean the Stolz angle would be something which just is such a region. No? Okay, but then we also truncate it at beta. No? So this means what I have here is really this region here. No? So I'm bigger than beta, let's use beta. Here's imaginary part is equal to beta, and those guys here are the straight lines which are defined by this equality. So alpha 1 is equal to x, alpha 1 is equal to minus x. Okay, so then that's the region, and that's essentially the region on which we can act with the Quotient transform. So this is now the replacement of the ball about infinity. Okay, and the R transform, I mean, for this we have to use 1 over set to see what it does about infinity, so we take a 1 over set of those guys, and this will give us a kind of wedge thing about infinity. Okay, so we define this, and then if I take 1 over sets which are there, then I get a different region, which is more wedge. So we define this and define kind of wedge, which I denote by delta, alpha beta, and this is just, those are elements in the lower half plane, which are just the 1 over set of the guys from there. So this means set to the minus 1 is in this truncated Stolz angle. Okay, and those guys, I mean, they are now in the lower half plane. So here's 0, and they are essentially looking somehow like this. And here, also I just have to see what happens with the boundaries of this domain by the mapping set goes to 1 over set. I mean, this line here, y is equal to beta, goes this guy here, and the other lines are going to something like this. So this is now this bounded region. So this of course is unbounded. This goes to infinity. This is bounded. This is the replacement of our wall about 0. That's where we can define the R transform in such domains. Before we could define the R transform in boards about 0. Okay. If you don't have compact support, then this is not true anymore in general, but at least you can do it in domains like this. So this is the alpha beta. Good. Okay, and then the theorem about the R transform is more or less that we can define the R transform of domains like this by as the solution of this relation between the Cauchy transform and the R transform. So let me formulate this in the next theorem. That's the starting point. I'm not going to prove this because this is, in principle, this is very much like our analysis which we did in the last chapter when we analyzed this equation and where it has a unique solution. And then we use this solution for defining the R transform. And I want to give you a precise statement. Okay, so we consider a probability measure, let mu be probability R, arbitrary one, and its Cauchy transform, we note G, its Cauchy transform G. Okay, then actually, we saw before that 1 over G is something which appears quite naturally in many equations, so maybe we also eliminate it. So this is 1 over G. This is really 1 divided. It's not the inverse under composition, but the inverse just under multiplication. So that's easy. That's also a nice object. And of course, this goes now from the upper half plane to the upper half plane. G goes from the upper half plane to the lower half plane. So this goes from the upper half plane to the upper half plane. Okay, and then the statement is that for every alpha greater than 0, there is beta greater than 0. So that we can define the R transform on domains like this. So we are not saying that there is one fixed alpha and beta on which we can define it, but we have somehow the freedom of choosing alpha. So alpha is the angle here. But then the beta decides how far we can go with it. Okay, so if it's getting wider here, then we have smaller beta. Good, okay, so there is for every alpha there is a beta, so that we can define an R transform as the inverse of this function under composition at 1 over set. So as usually, we go over from our functions, particularly the Cauchy transform, by 1 over set to function where things are defined in the neighborhood of 0. Cauchy transform is defined about infinity, so with this transformation we go over to this, and then the inverse of this is essentially given by this. Okay, and we have 2 sets, right? 1%. So we take this R transform, and this is defined, and it means of course that this inverse here is defined, for sets in this wedge region delta beta. And of course there we have the equations which we want to have between Cauchy transform and R transform. And we have, I'm saying that R plus 1 over set is the inverse of G, and we can write this in 2 ways. We can either take R as an argument in G or the other way around. And of course we have to write down the right regions where this makes sense. Okay, so the first is that G of R of set plus 1 over set is equal to set, and this is true if set is in delta alpha beta. That's where the R transform is defined. This R of set this is defined here. And then if I take R of z plus 1 over z, then I'm going over into a region like this, and there I can apply my Quotient transform. I mean, Quotient transform I can apply everywhere if I like. But for the other way around, it's getting more important. So I'm going to have R g of z plus 1 over g of z. And this is now true if I'm in such a truncated Stolz angle. Gamma alpha. So for this, I take domain like this. Then I take the Cauchy transform plus 1 over Cauchy transform, and this is then mapped into such a domain, and there I can apply my R transform. So this equation makes sense. Good. And of course, I mean, the point here is that we are again using this equation for defining the R transform. So in principle, we have to see that the Cauchy transform has a unique inverse, at least for domains like this. And the proof of this is more or less similar to the proof which we did in the compact case. I mean, in the compact case, we had here a ball outside of some boundary, and the R transform was for a ball inside. Then we had to see that the Cauchy transform maps such balls into each other, and we had to see that on some balls we find a unique inverse. Okay, and the crucial tool for this was this Rouget theorem. It shows us that we can control number of zeros if we deform equations. And that's the same what we are doing, one has to do here. So it's technically a bit more complicated. I mean, you have to control more these domains here. What happens if you are mapping? From which of those domains do you go to other domains, and how do the alpha and betas behave? But this can be done, but otherwise, in principle, the proof is the same as before. So I'm not going to give you details. So the proof is similar in the case of also which was 4.12. And again, the main or the crucial calculation there was to see that you have a unique pre-image of something. Okay. This means you have to have a unique solution of some equation, and this we saw that we deform this equation to a trivial equation. And then we have enough control so that Rouget's theorem tells us that the number of solutions is the same, namely exactly 1. Right? That's what one also has to do here. So that's really the analysis, the complex analysis tool which is being used. So again, using in a suitable domain. Good. Okay, so I don't want to go into this. Yeah, good. But then one has now, okay, so one can define the R transform, and in principle, you could now use this for defining the free convolution. So you would say, I have two measures, I can define the R transforms, and they are defined with regions like this. Maybe not the same region for both of them, but at least there's some intersection. And in this intersection, I can take the sum, I get another R transform, and this is then the R transform of some measure. This I call a free convolution. So in principle, I could do it like this, but then you have all those domains, they are changing, you are changing the measure, and in particular, yeah, it's not so nice to deal with them. So it's really good if you can go over to the subordination formulation and maybe describe everything in terms of such a subordination function. Okay, and that's what we want to do next. Good, but I think I stop here for today, and next time I will give you the main ideas how one can see that such a fixed point equation has, for all set in the upper half plane, a unique solution. But that's it for today.